Okay, hello everybody. So far in the lectures or in the previous module, what we saw was a typical response of a first order system to various test inputs. We also justified why we had those typical test inputs like an impulse, a step, a ramp and so on. We also saw the notion of steady state error while we were just introducing a response of first order systems. We even looked at response of second order systems, and we saw there are lots of other things to take care of while designing a second order system, like the peak overshoot, like the rise time, and then you had the notions of settling time and so on, right. And these were inherently related to the system's damping and also the natural frequency. Later on we characterized steady state errors of the system, and we saw how addition of an integrator or a pole at the origin helps in achieving a good steady state behavior, right, only in terms of error, right, not necessarily with reducing the settling time. And in all this analysis, what we had assumed was that the system was inherently stable, and for that analysis purpose we had just defined stability as a property where if the system is subject to some initial condition, it will regain its equilibrium position or its original configuration, right. So, what we will do in this lecture is to first formalize the notion of stability of a system, because before we even try to go for analysis of steady state or even the peak overshoot, what is important before any design is carried out on the system is that the system should be stable. Now, what is this stability, right? So, this is a very important property before we design a control system, right. So, let us see a couple of videos to just get a little idea of what this stability business is all about. And of course, so these are videos from these websites. Okay, so there is this guy driving and oops, so nothing is left for him, right. And you have this aircraft which, okay, so okay, by the way, this is not an animation video, this is something which could happen in real time, right. So, you have this big turbulence and then your aircraft behaves in a very abnormal way. Okay, so these are not just the two definitions, or these are not just the two pictures which define instability, right. Okay, so how is this characterized by the system? So, by the system we had so far said that the entire course would be on linear time invariant systems, typically with single input and single output, and what we had as the information of the system was essentially the transfer function. Now, we will see how the transfer function gives us some information on the stability of the system, right. So, the first definition would be a system is stable if the system comes back to its equilibrium state, sometimes even called the zero state, when the system is subject to an initial condition. And again, the simple example which we saw so far is the simple pendulum, right, with certain damping. So, if the pendulum is at equilibrium position, it will always remain at equilibrium position. However, if I start at some position, say which is somewhere here, say theta equal to some say 20 degrees or whatever, then I just so this is my initial theta, I just leave it, it will just oscillate and then come back to its position which is theta equal to 0, right. So, this is stable behavior when subject to an initial condition of theta equal to 20, the system regains its equilibrium configuration. Same thing happens when theta is say somewhere here or here or here and so on, right. Okay, now what is the meaning of then unstable, or what is the definition of unstable? A system is unstable if the output diverges without bound from its equilibrium state when the system is subject to an initial condition. So, let us do the reverse of the pendulum, right, here. So, I have this guy, right, okay. So, this is my pendulum, okay, not a very good drawing, but as long as it is in the upward position, it will always remain in the upward position, right. That is what physics tells us, right. Once you are in the equilibrium, you are always in the equilibrium position, right. Now, I say I do a very small perturbation or subject it to initial conditions, say theta equal to 1 degree for example, right. Then what would you expect is that the system does not go back to its original configuration, right? Just open loop system, there is no control, nothing. So, what it does, it just goes down, right, and then its energy increases quite a bit, right. So, okay, most systems it does not really go out of bound because of this physical limitation here, right, but mathematically we will say, well, the system is kind of going out of bound. So, this system with what we call as the inverted pendulum system is unstable in a way that, so if this is starting with this notion theta equal to 180 degrees, this is also an equilibrium position, but this is unstable behavior. And the system is marginally stable if it tends to oscillate about its equilibrium state when subject to an initial condition. Now again consider this simple pendulum without damping now, say theta equal to 20 degrees, right. So what will you expect? It will go to say minus 20 here and then come back again, just keep on oscillating like forever. So here the output or the system does not really go out of bound, it just remains within this nice bound of theta equal to 20. If I started theta equal to 40, it will just keep oscillating between plus 40 and minus 40 and so on. So these are systems which are called marginally stable, right. Okay. So stability also depends on the nature of input and how my system behaves to that certain input, right. So what we in an input output notion, stability is defined also as small changes in input should not lead to very large changes in output. Small changes in input could lead to small changes in output, that is acceptable, right. For example, here if I a small change in initial condition could be, well, I am going from 20 to 40, but then my output does not really go like, the behavior does not go to like say 400 degrees or something. Even here if I start from initial condition of 22, well, the output does not really change much, right, it is still very much within the desired behavior, right. Okay. So how do these bounded signals look like? Well, so this is one, the exponentially decaying signal is an example of a bounded signal. So it is kind of bounded in values. So you can also have a constant input, this guy is also bounded. Okay. A sinusoid is also a bounded signal, right. So it just does not really go up, right? And then okay, unbounded signals are one which just increase very large with time, right. So these guys just keep on increasing. Similarly these oscillations, right, the amplitude just goes on increasing with time, and these are essentially unbounded signals, right. So they keep on attaining very large values for large values of time. Okay. So in the case of input output, what we call as bounded input bounded output stability, or in short BIBO stability, a system is stable if for every bounded input signal the response should be bounded, right. Say for example, like I have a bounded input here, the response should just be bounded. If the response goes like something like this, then it is unbounded. Okay. So how will we define unstable systems in the input output setting? So if I find any one signal which is bounded for which the output goes unstable, the output goes unbounded, the system is unstable. There could be say 25 inputs for which the system behaves like this, but for the 26th bounded input, if the output goes unbounded, that system I would still call unstable, right. So a system is unstable if for any bounded input signal the response goes unbounded, right. So this is how it looks. So I have a bounded input, I pass it through an unstable system and I get a response which is unbounded. Right. So there is also a notion of exponential stability in linear systems. So what does this mean? That in the absence of input, or if the input is 0, if the system response asymptotically decays to 0, right, again within an envelope, then the system is called exponentially stable. For example, a response of say e power minus t is an exponential stable system. So okay, we will not go into the details of this, but just to make a side note that if I take a linear time invariant system and if I say that the system is exponentially stable, then it is also BIBO stable, right. So just the definitions of stability, what have we, how did we define stability? First is that the system, if it is subject to a non-zero initial condition, will eventually go back to its original configuration or the equilibrium position. The second notion in terms of input and output was, if the system is subject to small changes in input, it will result in small changes in output, or more formally, if the input is bounded, the output should be bounded, and if the input is bounded, output goes unbounded, I call it an unstable system. Okay. So let us see what that means in terms of what we have learned so far, in terms of the transfer functions or in terms of the block diagrams. So let us take the standard, I have a plant system here, I have a certain input or a certain reference generating a certain output C of S, right. And then the output we know in the Laplacian domain is given by C of S is G of S times R of S, or in the time domain we use the convolution property that C of t is integral G tau R t minus tau t tau. Okay, what do I know here is that the input or the reference signal is always bounded, right. So, this is kind of necessary, right. So, the input is bounded and then the magnitude of the output. So, I could just say, okay, so this C of t, if I just look at the absolute value of it, C of t is integral 0 to infinity G tau R t minus tau d tau, and I just take the absolute value to the inside, I get this one 0 to infinity G tau R t minus tau d tau. Now, this R I know is bounded, and let me assume that it is bounded by some number m, and this absolute value of this output C of t then takes this form. Now, I ask the question, R of t is bounded, when is C of t bounded? Well, the answer has got to do with this guy now, because I already know that R is bounded by m. So, the answer of when does a bounded input result in a bounded output lies in here, in this expression here, right. So, the output is bounded when this guy is also finite, or when integral 0 to infinity the absolute value of g is less than infinity, or it is bounded. So, and this guy is essentially the impulse response of the plant, right. So, the system is Bibo stable if and only if the impulse response is absolutely integrable, that the limit of this integral exists, or it is a finite value, otherwise it goes unstable. Okay. Now, in terms of the transfer function, we know that the transfer function is represented as the ratio of two polynomials in S. You can also write this in terms of the pole 0 configuration, right. So, how did we define the poles? The poles of the system are the roots of the denominator polynomial, for which ds, I equate ds equal to 0 and then find out what are the roots. Similarly, for the zeros, I equate n s equal to 0 and find out the values of h for which this equation holds true, right. So, this system here has n poles and m zeros, okay. And of course, the number of poles will always be greater than or equal to the number of zeros is what we will follow throughout. Okay. So, let us see with the help of an example, right. I have a system which is like this. So, I just look at the numerator, equate it to 0 and I just get two zeros, right, z equal to minus 3 and z equal to minus 4, and there are 3 poles, one at the origin, and I have a complex conjugate pair minus 1 plus minus j2. Okay. So, if I go to the S plane with sigma, S is typically like this guy, right, sigma plus minus j omega, right. So, it has the real values and the imaginary values. So, a pole at the origin would be, so this guy entirely goes to 0. So, I am here. So, pole is usually denoted by a cross. So, I have a pole here, complex conjugate poles at minus 1 plus j2 minus 1 minus j2, and two zeros, one at minus 3, one at minus 4, and zeros are usually typically. So, this is the notation for 0. Okay. Now, we will see what is got to do with stability. What has this locations here 1, 2, 3, 4, 5 guys, do they give us any information on stability? Right. So, that is what we will try to investigate. So, again the roots. So, the denominator polynomial ds going equal to 0 is called the characteristic equation of the system. So, we will do a little bit more of this later, but at the moment you can just assume that I am just interested in the solutions of the denominator equation ds going to 0, right. And then the roots are called as the poles, and if I assume for simplicity that the poles of the system are distinct, I can rewrite this from my Laplacian theory as like this, right. So, S minus S1, S minus S2 and so on, and these poles can be real, imaginary or complex, just that they are not repeated. We will come to the repeated case a little later. Okay. First, so let us take some partial fraction expansion of like this and say, well, I am just interested in this guy, or say one guy, say the pole is real, say Sk equal to A, then the pole lies in the left half plane for A equal to 0, right. So, it will be somewhere here on this negative line. Okay. Now, the inverse Laplace of this guy we know is A power k e power a t u t, right. And therefore, when A is less than 0, the pole lies somewhere here, I will denote it by a cross, and then the impulse response I know is something like this, right. It just dies down to 0 after, well, asymptotically it goes to 0, right. And this is actually a bounded output response, right. And hence, the system I would call is stable for A less than 0. So, my first observation I could make is, if I have a transfer function of the form A over S plus A and A lies in the left half plane, then my impulse response of the system is bounded, and therefore, by the first definition I could say that the system is stable. Okay. Now, similarly, when A is greater than 0, when A is greater than 0, my pole is sitting over here, and the impulse response is some constant A e power a t. A is greater than 0, therefore, I would expect this guy to keep on increasing, right. So, this is unbounded response. If t goes very large, this guy assumes very large values, and therefore, I can say that the system, if the pole is sitting on the right side, then my system is unstable, right. Second observation. Now, third observation, what if my pole is just sitting here? Okay. When A equal to 0, the pole lies at the origin. So, this guy, I just put a cross here, and then the impulse response is constant with time, right. Okay. So, this, the output does not increase with time. Okay. But however, if I just integrate for this case g of t from 0 to infinity, say g of tau d tau, then I see that the area, so g, this is essentially area, right, that this area is not bounded, right. The area is not bounded, but my signal does not really increase like it increases here, right. So, this system, the simple integrator or with the pole at the origin, is not absolutely integrable, and we can just call this as some kind of a marginally stable system, right. So, now we saw three things: what about a pole on the left, a pole on the right, and the pole at the origin, right. And then, okay, nothing to do with zeros so far. Okay, what happens if my pole is now complex conjugate? Well, and say there could be two possibilities, that the poles could, so this is my sigma, this is j omega, the poles could either be here or be here. Okay. So, if A is less than 0, then these are my poles, right, this is for A less than 0, and the poles are on the left half plane, not just on the left half real line, but on the left half plane, this entire thing. Okay. Okay. Now, if I just do all the partial fraction thing, then I get that the response of the system is given by e power a t cos b t plus phi, right. Okay. Now, this is a general expression no matter what the sign of A is. Now, for A less than 0, the poles lie here, and the impulse response, since this is e power minus a t is decaying, it decays exponentially to 0, indicating that it is also absolutely integrable, right. So, it will be something like this, right. So, this is integrable, this is the area is finite, the response is unbounded, and therefore, this system is Bibo stable, and of course, it is also stable by both the definitions for A less than 0. For A greater than 0, the poles are somewhere here on the right half plane, and the impulse response increases without any bound. So, it just does this, right. So, you see that the oscillations keep on increasing in amplitude, right, and this is an unbounded behavior. Okay. So, what if A equal to 0 again, right? If the pole Sk is imaginary and say I just have here, so 1 plus j omega and minus j omega, then the response is simply of the form A cos b t plus phi. Okay. So, the response I know is just a response of a sinusoid, it just be like this, right. You just have sustained oscillations, and therefore, I call this system to also be marginally stable, right. It neither increases unbounded in value, nor do the oscillations die down to 0 as in the previous two cases. So, this response or this oscillatory behavior is what I would call as marginally stable systems. Okay. So far what we have seen is, if there is a distinct pole like S equal to A, if A is less than 0 it is stable, A is greater than 0 it is unstable, A being equal to 0 has some kind of a tricky response, the output does not grow unbounded, but the system is not absolutely integrable. We could call this as a marginally stable system. If I have complex poles, I am just interested in what does the real part do. If the real part is less than 0, then the system is stable, real part is greater than 0, we see an unbounded response, and if the real part is 0, which means my poles are just on the imaginary axis, then I just see an oscillatory response. Okay, let us see what if now we have repeated roots, say I have say couple of roots at A, right. So, if I just to draw it here, this is my minus A or plus A here. Okay. So, my response would be some constant A plus some other constant times t e power a t, and again this depends on what is the value of A. If A is less than 0, then the impulse response is stable, and if A is greater than 0, then the impulse response goes unstable, and that could be computed quite easily. Similarly, if there are repeated complex poles, say there is a couple of guys sitting here and couple of guys at the same location here, then again depending on the sign of A, my system is unstable or unstable. So, this region is again the stable region when A is less than 0, and A greater than 0 is always unstable. So, the same thing holds, right. If the poles or the real part of the poles are less than 0, I am still strictly less than 0, I am still stable, and if they are strictly greater than 0, then my system is unstable. Okay. Now, earlier we saw something about the root at the origin, means something like 1 over S, or when the pole is at the origin, then I saw that my response was just some straight line, right. It was bounded in value, but not integrable. What if I have 2 of this, right? If I have 2 of this, my response would look something like this, right. It will just keep on increasing with time, and that is because of this kind of thing, right. A k plus A, k plus 1 some other constant time t, and if I just plot it with time, this is my response, it just goes unbounded with time. Okay. Now, let us take these guys further apart and say, well, I had a j omega, I had a minus j omega, and I saw earlier that this response is just oscillatory. Okay. Now, tricky things will happen when again I have multiple things here and multiple things here, then my response is A1. Okay. This is the response when there is only one pair of poles which are imaginary, and if a second guy comes, then I have this guy A2 times t cos b t plus 2 and then t square and so on. So, this response will actually keep on increasing like this way, and this also is an unbounded response. Okay. So, these two guys, as long as A is less than 0, A is less than 0 has a stable behavior, whereas these two guys has a strange kind of behavior, right. If there is one pole at the origin, then I am in some kind of a marginally stable behavior. If there are 2 poles at the origin, then I just go unbounded. Similarly for 3, 4 and so on. Also here, if there is one pair of complex pole on the imaginary axis, then I have some kind of a marginally stable or an oscillatory behavior, whereas this guy makes it unstable if there is more than one pair of poles on the imaginary axis, right. Okay. So, just to summarize, what is the relationship of the stability with poles of the transfer function? If all roots of the characteristic equation have strictly negative real parts, then the impulse response is bounded and eventually decreases to 0. This also means that this integral which I was trying to compute is finite, and therefore, the system is Bibo stable. If any root of the characteristic equation has a positive real part, it could just be 1, it could be 500 roots of the system, even if 1 is on the right half plane, then my system is unstable as gt is unbounded and this guy, this integral is not defined. Thus, the system will become an unstable system. Lastly, if the characteristic equation has repeated roots on the imaginary axis, right. So, again the same thing, it results in an unstable system. So, lastly, if one or more non-repeated roots of the characteristic equation are on the imaginary axis, then GT is bounded, okay, but the integral would not be bounded, right. So, as we saw here, this integral here is unbounded, just one root at, okay. However, if the input signal have a common pole on the imaginary axis, then CT becomes unbounded or the output becomes unbounded. And there are also cases where in the absence of any common pole, output is bounded and has sustained oscillations, like these two cases, right. Here I have sustained oscillations, or here is just a straight line, and these kind of systems are typically referred to as marginally stable systems. So, we have categorized stable, unstable and marginally stable systems. So, on the left half plane it is pretty clear, on the right half plane it is pretty clear. On the imaginary axis, if there is just one pair of complex pole, then there is some kind of marginal stability, but if there are repeated roots, then I go to an unstable level. Okay, to just pictorially say what I have said. So, this is stable region, left half plane, unstable, and this is the imaginary thing, right. So, where it could just be marginally stable, again depending on how many roots or how many repeated roots are there. Okay. So, what have we learned so far is to define the concept of stability first from a system response to a non-zero initial condition. We also defined bounded signals and studied or defined what is called the bounded input, bounded output stability, in which case we said if the input is bounded and the output is bounded, then the system is stable, or if there is any one bounded input which results in an unbounded output, the system is unstable. However, what we need to be careful is, what if the input is unbounded and the output is also unbounded? Can I say something about the stability? Well, the answer is kind of no, because if I am tracking a ramp, as we saw in some of our previous examples when we are doing the steady state error, my input is unbounded, right, it just t, right, it just increases with time, and the output is also expected to increase with time because I am tracking this signal back, right. It is an unbounded input and an unbounded output, right. So, there I just cannot categorize saying that okay, input is unbounded, output is unbounded, and therefore the system is unstable. No, we have to be a little more careful with that. Okay. So, what we did next was to relate stability to poles and zeros, well typically to the poles, and we said depending on the location of the poles, I can judge or I can say something about the stability or not of the system. So, now next we will see is, if I am given a polynomial of say some order 10 or 15, how do I compute its roots, or how do I at least say where the roots lie? I do not at some point of time need to explicitly compute where the roots are, as long as I know that they are somewhere in the left half, I am happy. Or they say there is one guy in the right half plane, I do not really know where he is, need to know where he is sitting, right. Even if he is at +1 or +100, it is still unstable. So, we will just try to learn some tricks called the Routh-Hurwitz criterion, which will tell us about stability of a given transfer function. Okay, thank you.